Let's look at a bit more detail about the mix layer. We already kind of defined it, and here we are showing at some mid-latitude location where even the peak surface temperature in August is only 14 degrees centigrade. But let's start here, let's say in January. There is winter, boreal winter in the northern hemisphere. So the surface cooling creates turbulent kinetic energy by density contrast. So the atmosphere takes up the heat and the ocean density gets heavier and the mixed layer just collapses and the thermocline almost vanishes, and maximum cooling happens in March, and then sun begins to come north across the equator. So by May you are beginning to re-stratify the water column. So the well mixed layer down to 100 meter is beginning to re-stratify. Suddenly you have a mixed layer that is just 40 meters. Okay, and the warming continues. By July the sea surface temperatures have almost doubled, so the mixed layer has become shallower because the thermocline has become much more sharp. How are the two related? Basically the gradient, the strength of this gradient below the mixed layer determines how much energy is needed at the surface in terms of the turbulent kinetic energy. Remember, it's a combination of the wind strength and surface cooling and heating, and the buoyancy in terms of freshwater forcing. The sharper the gradient, more the energy you need to mix. So as you warm, it's harder to mix, so the thermocline tends, or the mixed layer tends to get shallower. Thermocline is sharper, okay, and the temperatures are almost the same as soon as you go below the surface. The warming continues. In August you reach the peak temperatures and peak thermocline gradient, and as sun begins to go south after the autumnal equinox, you get well, autumnal equinox, never mind. After the summer solstice, already it's moving south. So the surface cooling begins, and by September you can see that the temperatures have cooled. The cooling has deepened the mixed layer, and the thermocline is still well defined, but the uh, November cooling is much sharper. You have gone from about 13 degrees to about 7 degrees centigrade. Mixed layer has become much deeper, and you are headed back to the winter mixed layer. So this is a rapidly moving animation here, but you can get a sense that the winter hemisphere tends to have deeper mixed layers at high latitudes. So southern hemisphere winter, northern hemisphere winter, and you can also see the contrast here. The mixed layer here is shallow, let's say 0 to 30 meters or so. In the west it's somewhat deeper, from 50 to 100 meters or so, and they have a strong seasonal cycle as well. This matters because as the upwelling gets stronger, here we are talking about heating and shallowing, right? Stratification by heating, whereas here upwelling creates stratification by bringing up cold water. So you can imagine that this cold water is being lifted up because of Ekman divergence. So then you need again turbulent kinetic energy at the surface to entrain cold water to make the mixed layer deeper. Entrainment makes the mixed layer colder and deeper. Okay, just get an intuitive sense about it. The other thing we'll see is that we have used this descriptor mixed layer very freely, and we have said that it creates vertically homogeneous profiles of temperature and salinity, but we didn't rigorously define mixed layer. It turns out that actually you can define it in terms of a criterion based on temperature or criterion based on density, typically not done with salinity. But here is a profile that is from some region, something like the West Pacific warm pool, where you have warm temperatures going down to about 70 meters, but because of the rain, let's say, the salinity is much shallower in terms of its homogeneous layer. So temperatures are constant almost down to 70, but the salinity is constant only down to 40, and that creates a density profile like this, because that's a combination of the temperature and salinity. So there is the d sigma. If you define mixed layer based on the constant density criterion, then you end up with a mixed layer here, even though the temperature is fairly well mixed down to 70 meters. So you end up getting this layer which is going to be entrained into the mixed layer when turbulent kinetic energy wants to mix up colder water into the mixed layer. Instead of mixing from the thermocline, in this case, the waters are mixing from this layer here, which is called the isothermal layer or a barrier layer. Why is it called a barrier layer? Because it acts as a barrier to mixing of the cold thermocline waters into the surface mixed layer. So whenever you have deeper isothermal layer than the isopycnal constant density layer, then you have this barrier effect created by the isothermal layer where entrainment effect is damped. Okay, that's why it acts as a barrier. It basically decouples the dynamics of the mixing with the thermodynamics of the cooling in some sense. Okay, so this actually turns out to be a very important player in many places, including the West Pacific, or in places like the North Atlantic where the hurricanes pass by. If you have a barrier layer and the isothermal layer that's deeper, and the hurricane passes by and wants to mix up cold waters, then it doesn't get as cold, which means the hurricane gets more energy. Remember, hurricanes take energy from the ocean and evaporation, and that's how they fuel their strong rotational circulation and so on. So if there is a barrier layer, there is a better, more favorable condition for strengthening the hurricanes, and they can last longer, etc. Okay, so special conditions of surface mixing or subduction of waters and so on. Subduction is a word we have not defined yet, but I think you have a sense. Water subducting under the mixed layer can create these kind of situations, a so-called barrier layer. Turns out to be important. It's not clearly mentioned in the book, but I wanted to introduce it because it is an important concept that you should know.